Okay, so today we're going to be talking about antiderivatives, which are what I would expect you think they are. So if you have a function f, we call it an antiderivative if when we take its derivative, we get the original function. So the antiderivative of little f is capital F, where notice that if we take the derivative of big F, we get little f. And this is just the typical notation that we use capital letters to denote the antiderivative of a function. So some of these you can do already. They're very easy to anti-differentiate. We can do them sort of in our head. So just imagine if you have a function and you know its derivative is, say, 2x. Can you come up with in your head what y must have been? So we're solving what's called a very simple differential equation because we're giving the derivative a differential. The differential is equal to 2x, and I want to know what is y equal to. So y is equal to some function, so that when I take its derivative, I get 2x. So hopefully in your head, you've already sort of said that you know that that would be x squared. And that would be true. So we just found our first antiderivative. The antiderivative of 2x is x squared. Now, you might quickly realize that that's not the only choice, because say if I said that the derivative of x squared plus 1 was 2x, that would also be true, right? So, or y equals x squared plus 7, or any other number, or even subtracting number, right? Y equals x squared minus 13. So in fact, there are an infinite number of functions that have a derivative of 2x, right? And they all differ by a constant, right? Plus 1, minus 13, etc. Okay, so we need a new symbol that we need to introduce, and it's going to be used to denote the collection of all antiderivatives of a function, right? So we just said that there's an infinite number of them because they all differ by a constant, and the collection of all of them will be denoted by, oh, sure, we're getting this software message, sorry. The collection of all of them will be given by this new symbol. So that new symbol is called the indefinite integral, and this is the symbol right here. It looks like a kind of skinny little s. And with the symbol, the integral symbol, we have the dx that goes with it. So this little part of the symbol, they go hand in hand. Like you're not going to have the integral symbol without a dx or a dy or whatever your variable is. So the x part here, that tells you that you're integrating with respect to x. So it's telling you x is your variable. This is called the integrand right here, and this is the portion that we're going to be trying to take the antiderivative of. So this symbol with the dx means to take the general antiderivative of little f. When I say general antiderivative, I mean to find the set of all possible antiderivatives, I'm sorry. So for example, with this integral symbol of 2x dx, we get x squared plus c. I don't know if you guys are seeing this little symbol here, sorry, but okay, so this indefinite integral symbol represents the general antiderivative of whatever function is here in that space. And so in this example, we see our general antiderivative is x squared plus some capital C, which is what we'll use to represent the constant of integration. Graphically, we see that this is just a whole family of sort of parallel curves that differ by a constant, right? So the purple here is the x squared function. If I shift it up 4, that would be another function that would have a derivative of 2x. If I shift it down, that would be another function that has a derivative of 2x. So all of these functions, all these curves, have a derivative of 2x. So if you think about it for a particular value, say at 0, notice that they all have a horizontal tangent line there, right? So they all have, I'm kind of missing here, they all have the same slope. And if you pick any value, so say at 2, if you were to draw the tangent line at 2 on all these places, and I'm obviously not drawing it very carefully here, but all of these would have the same tangent line slope for any given value. So this is what I mean when I say that these curves all look sort of parallel to each other. So if you were to collect all infinitely many of these curves, they are all that whole collection is the general antiderivative because they all have the same derivative. Okay, so let's look at some more examples. Now I know this is actually going to, notation-wise, going to differ slightly from your notes because I changed this in the notes to be the indefinite integral symbol, but I was having technical problems opening that version of it. So your notes looks like the integral symbol of 4x dx. So if I want to evaluate this, I'm looking for what function, when I take its derivative, do I get 4x. So you know that the power of x has to be up by 1, right? So it's going to be something times x squared. So think about what would you take if you took the derivative of x squared? You wouldn't be quite right. You'd have a 2x. So you need to have a 2 out front so that when you take the derivative, you get 4x. But plus, we always have this constant of integration. So 2x squared plus c is our general antiderivative. Okay, so all of these are ones that we should be able to do in our heads. So let's think about the next one. If I'm trying to integrate or find the general antiderivative of x cubed dx, I'm looking for something that when I take its derivative, I get x cubed. So if you think about power rule, we know that it has to be to the 4th power. And then I know when I pull down that 4 and subtract 1, I have to somehow be left with just plain old x cubed. If I take the derivative of this one, x to the 4th, I'm going to get 4x cubed. So what do I do to this expression to make it so that that 4 goes away? Well, I can put a 1/4 out front, or I could divide this whole thing by 4. So the other thing would be to write x to the 4th. That's supposed to be a 4 over 4. Both of these, if we add our plus c, gives us our general antiderivative. Now, if you're new at this, you should definitely practice to make sure you get the right value. So notice that if I pull down this 4 and take the derivative, I get back to x cubed. All right, let's look at the next one. If I'm finding the integral of x cubed minus 4x plus 1 dx, we already found the antiderivative of x cubed. And notice that since we're taking antiderivatives, it's going to behave similar to derivatives in the sense that if I have a subtraction or a plus sign here, I can still just treat each term individually. So the antiderivative of this polynomial will be the antiderivative of the first term, which we already know is 1/4 x to the 4th, minus the antiderivative of 4x, which we already know is 2x squared, plus the antiderivative of 1, which we haven't done this one yet. So what function, in terms of x, with respect to x, what function has a derivative of just 1? So that's just going to be x. And then again, we always remember our plus c for our general, to make it a general antiderivative. Okay, so we should continue to keep trying some more values, and every time you practice this, you'll get a little bit better. So I always start with the power, and ignore the coefficient for a second. So I know that when I subtract 1 from this one, I have to get to -3. So in other words, I'm adding 1 back to it. Now, as it's written, this actually will work, because if I pull down the -2 and then subtract 1, I get back to the -2x to the -3rd. So this is, in fact, the antiderivative. And if I add the plus c, I get the general antiderivative. Okay, let's look at the next one. I'm going to think of this as like 1/3 x to the -4th plus x cubed. Right, so again, thinking about with the power. If I add 1 to the exponent, this is going to be a -3. But this isn't quite right, because if I pull down a -3, I'm going to have a -3 there, and I want it to just be a third. So what coefficient could go here so that when I pull down the -3, I'm left with 1/3? So I think we're going to have to go with something like, if I did 1/9, then I would get a -1/3. So I need to make it a -1/9. So notice if I check by pulling down a -3, I'd get a positive 3/9, which reduces to 1/3. So this works. And then this term we've already done a couple times, so we already know this is 1/4 x to the 4th. So hopefully you're getting the hang of this, and what I would recommend you do is maybe try to do some of these before I do them by pausing your video and then checking to see if you get the right thing. Okay, so for f, we have, this is 1 over x cubed, which I'm going to view as x to the -3rd, because when we're working with powers, just like with derivatives, it's going to be easier to work with powers for antiderivatives. So if we add 1 to the exponent, we're going to -2, but that's not going to be quite right, so I need to cancel out this -2. I'm going to need a -1/2 out front. Notice now if I take the -2 down, it's going to give me the 1, so this will work. So there's my general antiderivative. Okay, and now let me just scroll down a little bit. Okay, this next one is a good one to do, because we'll have ones a lot like this. So sine of 2x, well, if it was just plain old sine of x, so maybe let me just do that for a second. If I just was trying to find the antiderivative of sine of x, I know that the derivative of sine is cosine, and the derivative of cosine is negative sine. So if I just said it was cosine, that wouldn't be right because I'd be off by a negative sign. So I have to put a negative there. Right, so now double check if we were taking the derivative of this. The derivative of the cosine part would be negative sine, and then times another -1. We'd get a positive sign. So this would work. So what about our example, sine of 2x? It feels like it should be kind of a negative and then just cosine of 2x. But if I leave it like that, that's not quite right. So, and you should definitely convince yourself that that's not right. So think about the fact that we have a 2x inside the cosine. So that's going to require a chain rule, where my inside function, my g of x, is 2x. So let's think about that. If I were to check, if I take the derivative of negative cosine of 2x, what am I really going to get? And again, you should convince yourself that this is true by, if you need to, just do the chain rule out. You would actually get a you'd get a positive 2 times sine of 2x. So you'd get twice as much as what we want. So we don't have a 2 here. And so to undo that, to get rid of the 2 that would be left, let's put a 1/2 here. Now notice that if you take the derivative of this expression, you get back to sine of 2x. Again, you have to make sure you really believe that. If you're just sitting there listening to me and not really understanding it, they're not doing everything you need to. So what I would actually recommend you do is pause the video, let g of x be your 2x, and actually work through the chain rule and convince yourself that you get back to sine of 2x. Okay, the next one we have e to the 4x plus, I'm going to write this as x to the 1/3 that I'm trying to find the antiderivative of. So again, we have sort of a chain rule idea that we're going to be undoing. So my first attempt would be to think that this is just e to the 4x. But the derivative of e to the 4x, again using chain rule, would get me back to 4 times e to the 4x. I don't have a 4 here, so I want to get rid of that coefficient by putting a 1/4 here. So I get 1/4 e to the 4x. Now for the second term, I'm adding 1 to the exponent, right? Because I know when I subtract 1, I have to get back to a third. So if I take 1 plus a third, I get 4/3. Okay, so this is my first guess, is to start with this exponent. But now when I bring this down, I would have a 4/3 here, which I don't, right? There's no 4/3 here. I need to make it so it's a 1. So I make the coefficient the reciprocal, 3/4. Now let's check it. If I pull down this 4/3, the 4 in the numerator and the denominator cancel, the 3 in the numerator and the denominator cancel, and when I subtract 1 from the exponent, I get back to 1x to the 1/3. So again, I add my plus c, and there's my general antiderivative. Okay, and then finally, this last one is cosecant squared. So I was not holding you responsible for remembering this one. So a more fair question for like a test would have been to say, what's the antiderivative of secant squared? Because we've taken the derivative of tangent enough times to know that the derivative of tangent is secant squared. Since this is in class or note-taking, it's not so hard for us to do this because we could just look it up. But it turned out that this would have to be negative cotangent of x, because the derivative of cotangent was negative cosecant squared, and so this would be the derivative. Okay, so we're going to pause for a minute here.